Humanity currently possesses over 12,000 nuclear warheads. When we picture the destructive peak of that arsenal, weapons like the 50-megaton Tsar Bomba, we naturally assume we are looking at an absolute, universal force of nature. But a nuclear weapon's defining characteristics, the towering mushroom cloud and the devastating shockwave, do not actually come from the bomb itself. When detonated, it releases immense thermal energy. That heat slams into the air, superheating the atmosphere to millions of degrees. The bomb just provides the spark. The rapid expansion of tightly packed air into a crushing wall of plasma executes the actual physical destruction. Which raises a fascinating question. If our ultimate weapon relies entirely on the precise thickness of our own sky to do its damage, what exactly happens if we trigger one out in the harsh extremes of the solar system? To test the physical limits of human power, we have to take our biggest bombs off-world. We start by completely removing the air. On rocky bodies like Mercury or Pluto, there is zero atmosphere. Without air particles to heat and expand, there is absolutely nothing to carry a pressure wave. A detonation in a vacuum produces no sound and no mushroom cloud. Instead, 80% of the weapon's energy is released as a silent flash of X-rays and gamma rays, instantly vaporizing the top layer of rock. With no sky to absorb the blast, all that kinetic energy gets driven downward. Because these planets have rigid crusts and dense metal cores, hitting one with a nuclear bomb is like striking a giant gong. The energy travels seismically, causing the entire planet to vibrate for hours. Those powerful waves ripple outward, converging on the exact opposite side of the globe. The concentrated force splits the planetary crust wide open. We know exactly how the lunar surface handles explosive energy because we've already run the tests. During the Apollo missions, astronauts actually brought grenade launchers and fired mortar shells at the moon to study its deep geology. Stripping away the atmosphere turns a bomb from an expanding crusher into a global seismic hammer. Now we test the opposite extreme. Venus has an incredibly thick atmosphere, carrying a surface pressure 92 times greater than what we experience on Earth. The air here is so dense, it behaves according to fluid dynamics. Setting off a bomb on the surface of Venus is structurally identical to setting one off 3,000 feet underwater. Back in 1955, the U.S. military detonated an atomic weapon deep in the ocean during Operation Wigwam. The immense surrounding weight of the water severely suppressed the blast radius. On Venus, a modern fusion bomb would form a brief bubble of glowing plasma in the thick atmosphere. Almost immediately, that high-pressure environment would violently crush and cool the bubble before it could ever expand into a shockwave. Under that level of planetary pressure, our most devastating weapon is swallowed whole and snuffed out like a match. If pressure suppresses the blast, scale renders it mathematically irrelevant. Jupiter has twice the mass of all the other planets combined. If you packed all 12,000 nukes on Earth into a single ship and fired it into the gas giant, the planet wouldn't even notice. We watched this happen in 1993. The Shoemaker-Lea comet collided with Jupiter, delivering a kinetic impact equal to 300 million atomic weapons. That blast vastly outperformed our entire global arsenal. It produced a few dark plumes that lingered for months, giving the planet a temporary atmospheric bruise, and nothing more. Moving to the outer gas giants, Uranus and Neptune, the dynamic shifts again. Here, an explosion acts less like a weapon and more like an extreme catalyst. Deep in the mantles of these planets, an intense thermonuclear shockwave strikes the methane-rich layers, violently tearing the molecules apart. With the hydrogen severed, extreme pressure instantly compresses the free carbon into solid diamonds, generating a temporary radioactive diamond storm deep inside the planet. Against the sheer size and exotic chemistry of the gas giants, our weapons either vanish into the storms or serve strictly as triggers for bizarre planetary weather. Despite this cosmic insignificance, some tech leaders still propose using nuclear weapons as construction tools in space, most notably the idea of bombing the Martian poles to release carbon dioxide and rapidly warm the planet. The physical reality of Mars guarantees this plan would fail. The surface is brutally cold and covered in fine dust. An explosive shock wave would kick millions of tons of that soil up into the thin atmosphere. That expanding cloud of dust would completely block out the sun. Instead of warming the planet, the strike would trigger a deep nuclear winter, while simultaneously vaporizing billions of years of irreplaceable climate data locked in the ice. In fact, there is exactly one scenario in the entire solar system where our nuclear arsenal serves a practical purpose, nudging or vaporizing relatively tiny incoming comets and asteroids to keep them away from Earth. We build these devices with the terrifying assumption that they are world-ending. But when tested against the vacuums, the crushing pressures, and the vast scales of the surrounding cosmos, they are completely insignificant. Our ultimate weapons are not world-ending, they are simply us-ending.